Okay, I'm going to go through the multiple choice first. So here is the first one. So compared to the first step in the proton-proton chain, the Coulomb barrier for the reaction of helium plus helium to beryllium is what? So the first chain is the proton, right? So one hydrogen plus one hydrogen. So you have two protons, right? So you have a +1 and a +1 that are going to repel each other. And then here we have helium that's got a +2 and a +2. So 1 times 1 is 1, 2 times 2 is 4. So this Coulomb barrier is going to be 4 times larger. Okay, the time it takes a neutrino to travel from the core of the surface to the sun is greater than, less than, equal to the time it takes a photon. So remember, we looked at light particles trying to make their way out of the sun, and it's this random walk that can take millions of years for the photon to come out. The neutrinos are only have the weak interaction, and so they can stream right out close to the speed of light. So actually the neutrinos make it out faster. So neutrinos are less than. Okay, so if beta decay is more rapid than neutron capture, then heavier elements build up slowly, resulting in elements that are called S process. So these are the ones that come slowly, are the ones that result when it's building up rapidly when you have a lot of neutrons. Which of the following elements are created predominantly in the cores of low-mass stars during their main sequence evolution? So I accepted, so basically I wanted you to know hydrogen is, created in the Big Bang. So that is not an option. Most of the helium as well is created in the Big Bang as well. But I would take that. That's okay for a low mass star, right? The sun goes fuses hydrogen to helium, and then you can also get in a low mass star helium to carbon, and some can even go on to oxygen. So those would be okay. In the main sequence, our sun will not get up to iron, and nickel is really something that's heavier in mass than iron and is created in the supernova explosions. Okay, which of the following elements are created predominantly in the cores of high mass stars? So same we had before. So we're going to have a hydrogen, carbon, oxygen, and then we're going to add iron as well, right? So this is, they get up to iron, and then you get the supernova explosion because you can't go beyond iron. Which of the following elements are created predominantly in the supernova explosion? So that would be nickel. That's the one we haven't used before. And then question 7, the diagram shows color magnitude diagram, which is the same as an HR diagram for 4 star clusters. Assume that all the stars in a cluster formed at the same time. Which cluster formed most recently? So along the main sequence, right, these are our high mass stars here, and low mass down on this side. And these high mass stars are evolving quickly, and they are going to die first, right? So this cluster has a lot more high mass stars. If we kind of look at the main sequence here, this is turning off, this is our color on the x-axis, right? So temperature is going this way. And then here as well, they're turning off, like the last of the main sequence ends here, whatever, somewhere between 0.3 and 0.6. The star is still in the main sequence here is a little bit over 0. Stars in the main sequence here are going even to minus 0.3. And then if we look over here, the main sequence is continuing up until almost 0, I'd say. So we didn't have to rank order them totally. We just want to know which one is the youngest. So that would be the one that still has the highest mass stars in the main sequence, and that would be A. And then, does the fusion of heavy nuclei require higher or lower temperature than the fusion of light nuclei? So it relates to that first question about the Coulomb barrier. But so the Coulomb barrier is going to be, K, Q1, Q2, if we just look at the potential energy over R. So as Q1 and Q2 increase, then it's going to get harder and harder for the nuclei to come together and actually fuse, right? So as this increases, the energy that you need increases, and therefore you need higher temperature, or you need higher kinetic energy to overcome the Coulomb balance or barrier. And average kinetic energy is 3 halves kT. Okay, so if we need higher energy, we need higher temperature. Okay, I'll do this one because this is the last one of sort of shorter answer questions. Okay, explain the meaning of each curve in the figure, making sure to explain the gamma energy. So this curve here, where E goes as e to the energy over kT, the negative energy over kT, this is the Boltzmann distribution. And this tells us the number of particles that have a particular energy. So as energy increases, you get fewer and fewer particles with that energy. Now, number of particles changes with energy. All right, so basically the number goes down as the energy increases. Okay, and then this one over here, that curve, EC over e to the 1/2, this is the probability for tunneling. And so tunneling is going to, so the probability for tunneling increases as the energy of the particles, oops, let me get rid of that, as E increases. So we have this kind of conflicting trends here, right? So that the number of particles that could tunnel, that would have enough energy to tunnel, is going down and down, right? And as the energy required goes up. And so when you look at the product of these two curves, you get this curve in the middle, which shows you where the most likely energies where you will actually get tunneling happening. I don't know what I did there. Most likely energy for tunneling, and that's the gamma energy.